Hello everyone, I'm Inigo Grajeta Formendi, and today I'll be presenting zkSENSE, a frictionless, privacy-preserving human attestation mechanism for mobile devices. This is joint work with Panos, Mateo, Antonio, Stan, and Ben, and it was performed while I was part of Brave's research team. So in 2019, the estimate of traffic that was associated with a user, but it was not triggered by a human, was around 20%. And it is expected that billions of dollars have been spent by tech companies due to these events. And is expected to grow even more, up to $50 million by 2025. Another observation of this type of studies is that more and more of these events happen on mobile devices or smartphones. So the current solution is CAPTCHAs and all the different flavors of CAPTCHAs, and we've all been annoyed at some point by having to find traffic lights or buses, and at some points even not knowing what we got wrong and when we got it wrong. So it is not really user friendly. Also, some studies have proved that image-based CAPTCHA or audio CAPTCHA or even semantic CAPTCHAs are not bulletproof, and there's been several type of attacks to undermine these mechanisms. And finally, one of the latest reCAPTCHAs presented by Google, mainly CAPTCHA v3, consists in using user data generated while browsing and sending it over to the server so that the server can compute a score of the level of humanness that generated this data. Of course, this has raised privacy concerns, as this type of data can be used to fingerprint and identify users. So our goal in this work is to kind of find a hybrid solution in between the two, in between the privacy-preserving image-based CAPTCHA and the seamless CAPTCHA v3 solution, and achieving both of the good properties simultaneously. So the key idea of our work is similar to what is presented by CAPTCHA v3, which is basically use some sort of action of the user, normal action of the user while using the device or while browsing, and using data generated while during these actions to detect to determine its humanness. In our case, what we use is the movement triggered by a touch event, and getting the data captured by the sensors at that point, figuring out whether it is a human or not. And as it turns out, sensors do distinguish humans. So note that on the right-hand side, the y-axis is not in the same is not the same as in the left-hand side. So even if there seems to be a lot of movement on the right-hand side, there's not so much compared to what happens on the left side. So the sensors react as we expect when we touch the mobile phone, which is all of a sudden they receive a sudden movement that we can detect. By using this, we can then determine whether a touch event was triggered by a human or a bot. And for that, we train a machine learning model. So an event happens, a touch happens, it triggers certain feedback from the sensors, and then we use this data in order to determine whether the user is a human or a bot. This sort of authentication is not novel and has already been presented in past work. And the main two directions that these machine learning human attestation solutions happen is, on the one side, the attestation or the evaluation of the model happens in the server. So basically, the user needs to send all its data to the server, and then the server will determine whether that data comes from a human or not. This has the same privacy concerns as CAPTCHA v3, which mainly consists in what can the server do with this data. The other line is basically to evaluate it locally and simply send the result. However, in a scenario such as Brave, where the code is open source, we can clearly not rely on something that is simply sent by the user, as a user could change the code and simply send I'm human constantly. Also, so one common problem of this type of solutions is that the origin of the data cannot be guaranteed. There needs to be some trust assumptions there. Some mechanisms presented in the literature assume that there is existence of a trusted platform module. Others simply assume that the data comes from the sensors, and the same happens with CAPTCHA-v3. At the end, when you use data of how the mouse moves or how the keyboard is touched, the guarantees of the origin of that data can only be given as much as the application itself can give. Our work is not an exception to this, and zkSENSE does not give any further guarantees of the origin of the sensors. Okay, so our goal in this work is basically to follow this one line of thought of human attestation through ML, which consists in evaluating the model locally. And in order to avoid these trivial attacks where the adversary simply gives a result which does not correspond to the score of the model evaluator over its data, what we do is we build a cryptographic proof that convinces the verifier, in this case the server, that a certain score is the result of a given of some private data evaluated over the model chosen by the server. So basically, the server defines a model, which is a model that we train, and then the proof that the user simply generates a proof of this score is the result of your model being evaluated over my data. Some particular properties of this type of proof is that it does not disclose any information about the input data. Mainly, it does not disclose any information about the input sensor. That proof is sent to the verifier, to the server verifies the proof and is convinced that the score is the computation that we just discussed. And if the score is above or below a threshold, then it can take the decision of whether this is a human, this is not a human. Again, this has not been the first time that it has been researched in the literature, and as a matter of fact, there are other previous works that study the possibility of evaluating a model locally and then only sending a proof of correct evaluation. However, the concerns of these problems is of these works is that the computational requirements for the prover are way too high for us to evaluate the model and prove correctness in a mobile device. So they are not useful for our use case, and we need to build our own ad hoc cryptographic proof. So how do we train our model? To do so, we slightly modified the Brave browser such that it stored data after touch events were triggered, and then we used the data to train the model. So of course this was not done over the main browser, but rather over non-public Brave browser modification, which we shared with 10 volunteers. And the app was used for more than 20 days for normal browsing activity. So with that data, together with automated data, which would mimic the actions triggered by bots, we trained different classifiers. And then we used 2 scores to determine which was the most appealing classifier for our use case. One is the F1 score because our data set at the end was unbalanced, and then the other one is the recall because what we're interested in, after all, is knowing how many bots do we detect out of all the bot events. However, those were not the only 2 factors that made us choose one classifier or another, because we also need to build this cryptographic proof. So ideally, we would use a classifier that building this cryptographic tool is as simple as possible. And for instance, decision trees or random forest, what you need to do in order to evaluate it privately is that you need to go through the different branches and constantly prove that the path that you've taken is the correct one. And to do so, we needed to use several range proofs, which turns out to be not very efficient at the level of requirement that random forest or decision trees request. So the number of range proofs for those type of classifiers were way too high for generating viable solution for mobile devices. Another example are neural networks with ReLU activation, so nonlinear activation functions, whether ReLU or any other, as is after every matrix operation, so you need to evaluate a nonlinear function, then all of this adds up, and the resulting computational overhead that we cost the user is way too high for our standards. So yeah, we had that. We took that into account as well, how easy it is to build a cryptographic proof, and we concluded that the best solution or the best classifier was the SVM, the SVM with a linear kernel, as the scores were reasonably high, and the overhead caused by this mechanism was the lowest. So, proving correctness. How do we prove, or what are the goals for the user proving correctness? So, first of all, we want to drain as less battery as possible. We want this to happen in a short period of time, because at the end, that period of time is the time that the user is going to have to be waiting until proving that it is human. And finally, we want the communication complexity to be low. After all, this is aimed at mobile devices, and not all users have infinite data plans. So reducing the communication overhead is crucial. To build this proof, which we named zkSVM, because zk stands for zero knowledge, which we'll see now in a second what it means. So to build zkSVM, we use two foundational building blocks. On the one side, we use zero knowledge proofs, and then we use commitment schemes. So a zero knowledge proof is a bit on the lines of what we discussed before. It's a proof that allows a prover to convince a verifier of a particular statement without disclosing any other information other than the fact that the statement is true. So for the more generic case of zkSVM, this would be, me as a prover, I'm capable of proving that this is the score related to the SVM model evaluated over this private data without disclosing any information about the private data itself. However, to build the more generic zkSVM, my video just got blocked. Okay, so the zero knowledge proofs that we use to build zkSVM proof statements, which are a bit more granular than this, but the idea is the same. And we use several proofs that we list and we explain in the paper, but the main proof that we use is one to prove that C is the inner product of two vectors A and B. And this proof that we use comes from a paper of Bunz et al., which was presented in S&P 2018, in which they present an inner product proof that convinces about this statement, mainly the inner product of A and B is equal to C, which has communication complexity logarithmic with respect to the size of the vector. This is very important for us because we need to reduce the communication complexity as much as possible, and given that our vectors are large, having a superlinear communication complexity for this statement is of utter importance. However, in the paper of Bunz et al., they didn't require the information of the vectors or the result to remain private. So basically they presented an inner product proof which did not have the zero knowledge property. In our paper, we make the necessary changes in order to make it zero knowledge, and we also prove that indeed that converts it in zero knowledge. The second building, stamp zero knowledge. The second building block are commitment schemes, which is basically a cryptographic primitive that allows an entity to commit to a value without having to disclose it, and ensuring that it cannot change its mind or change the value thereafter. What we commit in our scheme are the vectors. So again, we need a commitment scheme that commits to the vectors in as compact as possible. The perfect mechanism here, or the perfect construction, is the one of Pedersen commitments, which allow us to commit to a full vector into a single elliptic curve point. In our case, with the curve that we use, this results in 32 bytes per commitment, regardless of how large the vector is. And another crucial property of Pedersen commitments is that it is additively homomorphic, meaning that the commitment of a vector A plus the commitment of a vector B equals the element-wise, so the commitment of the element-wise addition of these two vectors. So by using these two building blocks, we are capable of building zkSVM. Mainly, we are capable of proving that a particular score is the result of evaluating an SVM model over a committed vector or over multiple committed vectors. In the paper, we proved that zkSVM provides data privacy, meaning that no information whatsoever of the sensor data is leaked other than the fact that it generates a particular score. Similarly, we also proved that zkSVM provides verifiability, meaning that the verifier is convinced that the score is a result of evaluating a particular SVM model to some list of committed vectors. So it's important to note here that zkSVM does not provide any guarantees of the origin of the data. It only provides guarantees that the score corresponds to the evaluation of a particular SVM to a list of committed vectors. So we implemented this in Rust for zkSVM and using Android SDK for the broader zkSENSE application. And we evaluated over two devices, a mid-end device, Samsung Galaxy S9, and a low-end device, Samsung Galaxy J3. So the latter is connected to Battery Lab, which allowed us to have more precise information about the battery consumption. The first Galaxy S9 was not connected, but we expect the battery consumption to be lower than the one of the Galaxy J3 for two reasons. First, the CPU computation is much lower for the case of the mid-end device, and also the computation time is much lower, by an order of magnitude lower than J3. Not only that, but the battery of the Galaxy S9 is also contains more amperage than the Galaxy J3, so the percentage of battery wasted will be even lower. Nonetheless, 0.2% is an acceptable battery consumption amount for this type of attestation. However, we see that in the running time, 3 seconds for Galaxy S9 is acceptable, 40 seconds for Galaxy J3 is not in the limits that we consider valid for attesting humanness. Communication bandwidth is good for both, it just contains the size of the proof. And yeah, so with these results, we show that we presented a seamless human attestation mechanism which provides privacy to the user and convinces the verifier that a score is indeed the result of evaluating a particular SVM model. So we presented a zero-knowledge proof of ML evaluation. It is small and battery efficient for both mid and low-end devices. However, we saw that it is a bit too slow for low-end devices. We also didn't resolve the problem of data origin, and we explored the possibility of using trusted hardware, but this is not widely in use yet, so it was not a possibility for our solution. Similarly, we want to improve the ML model to reach a broader audience in which for instance, visually impaired users are capable of still using this attestation mechanism by leveraging the sensor data when, for instance, the volume or power buttons are triggered, which are usually the buttons used mostly by these users to navigate through the smartphone. So I hope you enjoyed the presentation. Sorry I rushed up, and I'm happy for any question. Thank you.